Good morning. My name is Bill Kornfeld. I'm speaking to you about extending data lakes with Lambda and other real-time architectures. My co-presenter is Payman Moajarian. I'm the director of R&D at Think Big. We're a Hadoop consulting firm, and we became part of the Teradata family kind of last year. Payman is with the big data kind of center of excellence of Teradata. Okay, so we're going to talk to you about some considerations for choosing and using real-time architectures and also use cases for real-time architectures. Okay, just briefly, we're going to talk about what does it mean to be a real-time architecture, what are the use cases that are appropriate for real-time architectures, times where it would actually be a mistake to use a real-time architecture, and various design patterns, including Lambda architecture for real-time architectures. Okay, so the first question is, what does real-time mean? And as I mentioned, I kind of work for a Hadoop consulting firm, and what I find that the definition of real-time for most people in industry is faster than they've got now. Some people think that if you process the data sometime the next day, that is a real-time architecture because they're currently waiting kind of weeks to get their reports back. That's not the definition we're going to use today. So more broadly, whenever you have an architecture, you've got some data in and you've got some information coming out. And the blue box I marked data store, but it's kind of Hadoop. It's databases, it's some collection of servers kind of doing something. And this can be either for kind of push or pull kind of use cases. A pull use case is where you ask, what is the value of something that has been ingested? And a pull is, I've seen the following circumstance come up and I want to trigger some event outside of the architecture. So it really doesn't matter whether it's push or pull, we want to include both. And what we're, for purposes of this, real time is, kind of when data comes in to when information comes out, that's what we're measuring. So let's see. Yeah, so and for, it seems to be switching even when I don't push the button. Anyway. For purposes of this, kind of real time means, kind of a couple of seconds, up to a couple of seconds. So data comes in, an event gets ingested into your cluster, and then you can react to it in some useful way a couple of seconds, within a couple of seconds. So that's what we mean by real time. Okay, now there are okay. Okay, hopefully it'll stay there. So there are two general classes of information that we can store and retrieve, and I've kind of broken them up into atomic and aggregate. And examples of basically an atomic information is one unit of information comes in, and there is some semblance of that unit that you will find and you can retrieve kind of later on. Where aggregate information is, it's kind of coming in and it's being aggregated with a bunch of other information, and the individual events may not actually be present in any real way, kind of in the information coming out. So, example of atomic is you got a prescription record. So at this time, this doctor prescribed this drug for this person. That goes in, and at a later time when you come out, you can find out, you can find information about that particular prescribing event. An example of aggregate data is where you just know, well, the number of prescriptions for penicillin or the number of prescriptions that this doctor wrote in a given unit of time. So those are two kind of different classes of information you can store and retrieve. Let's see. It's going by itself. Okay. So it's atomic. And so atomic, well, I won't risk going back. So atomic data it can always make sense to kind of do that in a kind of real-time architecture. So if I have an event about a kind of a prescription going in, then it always makes sense to say I can retrieve information about that event within a second of putting it in the cluster. That is always a well-founded concept. With aggregate retrieval, it may or may not make sense. And that's in a lot of the analytics that we do with Hadoop clusters is aggregate analytics. And so it's important to understand kind of where it does make sense and kind of where it doesn't make sense. And I'll show you examples. Okay, so first here's a place where kind of aggregate information kind of does make sense, where you're kind of summing and counting things. And examples might be if you're kind of building the analytics for, kind of for an e-commerce website, that the kind of dollars of revenue kind of earned so far today. And so people are continually buying things, and you could see on a counter on a screen that said, as of this moment, we have sold, $3 million worth of inventory today. So that is something that definitely makes sense. Another thing that makes sense, another thing that makes sense is the number of, kind of the number of prescriptions that were written. But let's take a look at some cases where it does not make sense. A very important class of aggregate data that you want to report on are ratios. That, again, the example of kind of the e-commerce website, like a very important metric is the conversion rate. What percentage of people actually, who went to your website actually bought something? So, kind of how is that computed? Well, if you look at the picture, you've got, the little blue dots are basically, kind of people coming to the website. It's an event that indicates somebody has looked at a page on the website, and the kind of orange stars are conversion events. And what we want to do is we want to take a ratio of those two and kind of know what the conversion rate is for the website. So this certainly makes sense, kind of, if I count up all of the people who came to the website today and count up all the conversions today, I've got a well-defined number, I've got a well-defined ratio. But think about what this means kind of in real time. So what you have is now is a particular event, and at any given moment, nobody is coming to the website, nobody's buying anything. So what you really have to do is you really have to pick a range, and then you pick a range and you say, for that range, I can compute this value. But that range is no longer happening at a particular point in time. And so what people often do is they will, pick kind of a moving window over their data, and they will take a range of that data. And that kind of, that is certainly a well-founded thing to do, but it does not, let's see, somebody thinks I'm not talking fast enough, so it's advancing the slides, I think. So it's a well-defined thing to do, but you're really not telling the value of this metric at this moment. You're basically mentioning the value of this metric at some undetermined point in the past. And so you could use a real-time architecture to do this, but it's not really doing you any good. And one of the things that we have kind of noticed is that if you have, you can use a batch architecture to solve a problem. You can use a real-time architecture to solve a problem. The batch architecture is more efficient. You can get more done with less hardware if you do it in batch than if you do it in real time. So it's important to kind of determine whether you really need to use kind of real time to solve your problem. If you don't, then you're better served with a batch architecture. And furthermore, the tools and technologies for batch have been around for years. They are very stable. They may be a little boring. Everybody's always complaining about Hive and how boring it is, but it is very stable. It works. It does not have very many bugs. But if you look at the later kind of more real-time architecture. You look at Spark. I mean, Spark is a wonderful tool, but there are constant kind of bug fixes going in, constant revisions because of problems using it. So not only will you use more hardware, but you're probably going to have you're probably going to be kind of facing kind of difficulties, limitations with the tools you're going to have to do workarounds for. So it is useful to kind of decide whether a batch architecture would solve your need, and only go to real-time architectures if that's not the case. So let's look at another case of using real-time architectures and kind of questioning what the value of a metric means. Let's see. It keeps advancing, and I'm going backwards. Okay. Okay. So in this case of... Okay. Okay, fine. So in this case, we want to do kind of unique user counts. So again, you have people coming to websites. It's a very common metric in web analytics. People come to the website, and you want to know how many people came to the website for that day. Now again, that's kind of a very well-defined, that has a very well-defined meaning if you look at it as a batch aggregate. That you have any number of people that came, and so you can simply look at this list of people, you can find the unique values of that list, and you can report for a period how many people kind of came to your website. Makes a lot of sense, very easy to compute. But many people kind of are actually now, and I will not mention some products, but some well-known kind of website analytics products that actually claim to have a real-time version of this metric. And think about what that could possibly mean. So it's saying at the current time, so many people, 1,237 people are at your website. But they have no way of knowing that, in fact, because all they know is each time a page view has been rendered on a browser. So they know when somebody has actually kind of touched a page, they have no way of knowing if this person who looked at a page 10 minutes ago is still staring at that page. Absolutely no way of knowing. It is, as a metric, it is meaningless. And so I kind of caution you if this is the kind of thing you're looking at, if you go to kind of a real-time kind of meaning of this, or if you try to go to that thinking that you're learning more about what's happening at the site at this moment, in fact, you are learning nothing. So advance, please. Okay, now here's a case where you can have a problem that you can solve with a kind of real-time metric, or you can solve it in batch. But if you try to solve it in real time, you're going to use significantly more resources. And so let's say you've got a kind of web server, and you've got data coming back. And you can tell from the user agent field kind of whether you're dealing with kind of a PC or a Mac. And so that's kind of one of the things you want to know. And let's say you're dealing with kind of registered users, and they kind of told you what their gender was. And so you know kind of whether they're kind of male or female. And so what you want to know is you want to know the number, the number of page views, let's say, of PC users who are male, the number of page views of PC users who are female, the number of page views of Mac users who are male and Mac users who are female. And then you also want to know the number of PC users, the number of Mac users, the number of males, the number of females, and you also want to know kind of a page count for everyone. So think about what happens if you were doing this as a real-time architecture. So an event comes through. You look at it, you decide which category, which of the four categories it goes. So let's say it's a PC user who's a female. So you'll increment the register for PC female. You'll also increment the registers for PC, the register for female, and the register for everyone. And so you've just gone and you've incremented 4 registers. I mean, it doesn't sound like a lot, but just imagine millions and millions of these events kind of pouring in a very short period of time. Now let's consider what would happen if you were going to do this as a batch architecture. Well, the data comes in, and you would increment kind of PC female. The one thing, you'd increment the most specific place you could, and then at the end of the period, you'd look at how many PC males were, how many PC females were, and then you do a single addition to get the number of people who are on PCs. Similarly, you do a single addition to get the number of people on Macs, the number of people on male and female, and also then a single addition to get the number of people or everyone. So you have, and you can imagine, and we often do, if you have sort of elaborate product hierarchies that are much, much deeper than this, where you have like 8 or 10 different levels, you're basically incrementing registers at every level in this hierarchy in order to be able to report this information in real time. Now, maybe it's important to you, and if you need to do that, then you have to you have to go through the additional overhead. But if you do it in a batch architecture, the overhead is much, much less. So that is also a consideration to think about. Next slide, please. Yeah. Actually, why don't you just go on one more? Okay, so here's a case of something which kind of seems like you should be using a real-time architecture for doing it, but actually you don't need one. And this is something that, I picked this website, not that I personally had anything to do with the recommendation engine, but it's a fairly common, for this website, but it's a fairly common thing to see kind of in e-commerce websites, that you're showing a product, and then you've got a bunch of products at the bottom, which are kind of recommendations. Now, recommendations in the more sophisticated recommendation systems, they are actually based not just on the product you're showing, but also characteristics of the person who is kind of viewing the product, and also kind of where that person has been most recently. Some of the best signal for deciding what to recommend to somebody are the other products that they have looked at most recently. Basically, so the page comes up, and within kind of about 50 or 100 milliseconds, you have to kind of put up some recommendations, and that kind of sounds pretty real time. But let's look at how these systems are actually put together. Like when you only have 50 milliseconds to do something, you're not going to do a lot of computation. You're kind of limited amount of computation, and so what you do is you basically build a model, and there are different kind of different theories as to, kind of what kind of model to build, but let's say it's some kind of logistic regression. So you have kind of a bunch of features, you plug it in, and then it'll tell you, it'll be able to kind of score different things that you could recommend, and then you kind of pick the highest one. That's one way of building a system like this. And so what you do is basically you've got the data about past history, and you use that data to rebuild the model. You use that data to rebuild the model, kind of every so often, like maybe once an hour. It kind of depends on the nature of the things you're selling. But once an hour, once a day are kind of typical things. But then the model is basically used by the web server itself to sort of say, okay, well, here's the facts we know about this person. You plug those into the model, and you get the data back out. And so there actually was no kind of real-time kind of big data architecture in use here at all. You don't need Storm or Spark to build something like this. It basically is, kind of fairly sophisticated behavior that kind of seems real time, but in fact, there is no kind of real-time big data architecture involved. Next slide, please. Right, so basically, if you have to decide, should I use kind of a real-time architecture or not, consider the things I was just telling you, that sometimes real-time its meaning is not defined, sometimes it's more expensive, but nevertheless, you may actually still need to use kind of you still may have a use case where you need to kind of report on something real-time. And so really the question you need to ask is, do I need to know something and react to information within like a couple of seconds of something happening? And the answer may or may not, maybe yes, kind of maybe no. Example, again, the kind of prescription example, if a doctor puts in a request for a prescription and it goes in, and then moments later, you were just talking to the doctor on the phone, and then you're immediately, kind of at the pharmacy, you want to fill it, it had better be that the pharmacist will see that immediately. So that is a very, very good example of, a place where, it would need to be real time. But on the other hand, if you were collecting information about SAT scores, people taking the test, well, you may have just gotten a message that this person got this on the SAT, but if you can't report on that within a minute or two, it's probably not a problem. So those are the kinds of considerations. Next slide, please. Yeah, I just went through this. Next slide, please. Okay, now back to the Lambda architecture. So the idea of the Lambda architecture is the data comes in, and you break it into kind of two streams. One is, basically goes kind of batch, where you basically kind of take it and you store it in time partitions in HDFS, assuming that you're using Hadoop. And the other is kind of the streaming portion, where you're injecting it. I mean, the Lambda kind of came out of Twitter, where Storm was kind of the popular, and so you kind of inject it into a Storm topology. And in both cases, batch and streaming, you kind of process the data in some way, and then you put it in some place where you can access it. And makes a lot of sense. It actually kind of has, if you look at kind of the caveats I was giving you earlier, it says, well, there are some cases where you might want to have kind of streaming analytics, some places when you want to have batch analytics, and the Lambda architecture actually kind of gives you a way of doing it. And then the streaming analytics is placed in one place for serving, the batch analytics is placed in another. So the way it has been actually promoted, though, is, and I think this kind of comes from kind of the earlier days of Storm, is that, well, streaming is kind of unreliable, and so you kind of want to have the batch as kind of a backup for the streaming. But anyway, this is the Lambda architecture. Next slide, please. Okay, so somebody kind of looked at this and kind of said, well, all the streaming stuff, all this, kind of streaming stuff is not really all that unreliable, but, occasionally it could be. And so what we're going to do is we're going to put Kafka kind of in front of it. And basically what Kafka is it allows you to kind of unwind. I mean, it's kind of a publish and subscribe system that kind of stores a certain amount of history, and it can be quite a lot of history because it's kind of disk-based. And it allows you to kind of unwind. So if you should have made an error kind of in your streaming analytics, then you can always unwind and recompute. And then you've got something simpler, which is a pure streaming architecture. But if you heard what I said earlier, streaming architectures are often not the right way to go, not the most efficient or even the most well-founded way to go. Next slide, please. So this is something that we have been kind of building with, which we call the Mu architecture, where, like the Lambda architecture, you have a streaming component, you have a batch component, but there's no reason why you have to go to two different places when you want answers. And so if you look at the serving layer, I mean, something we commonly use is HBase. And HBase has kind of bulk, you can kind of bulk upload data, and you can also have individual events kind of trigger changes in memory. And so it's kind of Lambda-like. It's simpler than Lambda, and then the user really only has to go to one place to get the information. And the data that is best computed batch, you compute best. What's best computed streaming, you compute streaming. Next slide, please. Okay, so let me pass the baton to Payman, who will tell you about some specific applications.
So yeah, in terms of the real-time use cases, I'm covering two general use cases that are not very specific deployment, but generally speaking, that's what we've done in the past around. One is around Lambda architecture, and another one is called event-driven architecture. The Lambda one is more around medical records and patient records and how real-time can play a role in a Lambda specifically in that use case. And then the second one is more around customer data and how in an e-commerce website, you want to track things as events rather than doing batch type of a processing. So next slide, please. So the use case for the Lambda in the medical field, this is a case where You have patient data. You have challenges in terms of the nature of the data. It's wide. It's not very deep. But then you also have a mix of unstructured data, structured data. For example, HL7 data format. Some of it could come in a batch. Some of it is medical notes that coming in a streaming cases. And in all of these, you need to do some type of a surgery or something that's critical, and that information needs to be accessed in a more timely manner. It's lots of events, just like the event architecture that I mentioned later. And it's different languages, and there's different components to this architecture. Next slide, please. And this specific project was more around doing natural language processing on this data as part of this medical information that would come in. For example, notes from doctors, and you want to be able to decipher different types of information out of it that may be pertaining to a surgery that will come up. Or other types of notes unrelated to that, but essentially HL7 data that you are going to process. And the data comes into a RESTful manner that I'll show in the next slide. Next slide, please. So this is the overall architecture of this. And this is not a specific deployment right now. This is based on something in the past. It's one iteration of that architecture, which is what you see at the bottom is a message queue that all these events, whether they're batch or real time, get captured into that message queuing system. It could be a Kafka. It could be any type of a messaging, IBM MCQs, or any other type of queue that can handle the volume of data that this customer was dealing with. And then they get consumed. If there's real time, it goes through a storm topology, and some of the transformation happens real time. If it's batch, then it goes through the Flume in this case, and then gets captured into HDFS directly. In this use case, the serving layer is the Elasticsearch. So that's the layer. So you can think of this Lambda and to some extent also Mu, depending on exactly how you look at it, because at some point that Elasticsearch can capture both the data from the real-time system and from HDFS, so you can index them. And in terms of what happens in the NLP processing, that in this use case, that's sort of on the batch side of it, and it gets done after the data capture on the right side and toward the top. So really the serving layer in this use case is the RDMS database you see on the top, which is the result of all the NLP processing that gets done on the medical data. And some of the data is also being served from the bottom up, from the Storm directly to the BI tools. And that is, again, a blend of real-time and a batch to be displayed in a dashboard or some kind of registry or some kind of a reaction point-of-care tool system. So at a high level, this would be one way you could architect a system that, depending on how the data coming in and depending on what type of processing you need to do on it, you have different, and some of that NLP could in the future be done in Storm itself. So some of that batch processing, depending on the nature of that processing, could be moved toward the left side of the diagram. But really, it gives you that flexibility to, for example, that rule engine, a lot of that is being done in a batch mode, but an architecture like this would allow you to move it to different formats or different areas depending on the nature of the data and your SLAs or use cases. Next slide. In terms of some of the metrics, and these are not that relevant anymore, but these are some of the numbers that this use case was dealing with: 1.5 million documents per hour, 140,000 messages, and then these messages were being annotated, and the system that was built using this architecture is 6 times faster what they had before. It's really, in terms of the volume of data, is not really that large, but the architecture and the components there are able to scale to much larger on a need-to-have basis. Next slide, please. No, in this case, we're not. But in terms of what the hardware they use in this case, if you just want to know a little bit, it's a Teradata appliance that they use, which initially was HTTP 1.3.2 and now on a 2.1. So Storm was running on edge nodes, and then some of the other processing was really outside of that project that we worked on. But yeah, it's really the big data portion of it was a Teradata appliance. That's why we were involved. This is the second use case, which is around event architecture. This use case is a little bit more higher level. It's not a specific deployment that we have, but it's sort of in regards to how you do in a .com world or e-commerce website, how do you start looking at behavioral data? So you have application in silo, you have customer interaction, you have mobile application, social media, and you want to be able to, instead of having these applications be in silos in relationship to the customer, be able to have a picture of how these different applications, how the user or the customer is interacting with all these different apps that may not interact within each other, but be able to capture the different events, different interaction or behavioral exchanges that the customer does with each one of these. And again, some of these could be a display ad, some of it could be within your website, they could be uploading something, they could be viewing a picture. So this could be, it's a very holistic approach of looking at how do you follow a customer, a potential customer from different channels, from the mobile app and different forms, display ad, and how do they end up coming to your site, surveys or different types of interaction that they end up doing. Next slide. Next one. Next one. So this is really the end goal is really to create this kind of a what we call a data fabric, a thread. So this is a thread that goes, it's not really a time series chart you're looking at here. These are events throughout time, like the day one, they looked at the page search, they landed on the page. Then on day 3, we send them an email. On day 5, day 7, they did some other type of interaction with us. And again, these are across many different domains. So some of it is display advertisement, could be something on Yahoo's website. What happens in day 3 is interaction with our domain. But essentially, you're trying to create a behavioral data fabric of putting together, stitching together events that happen throughout time and be able to show that to in a dashboard mode. Next slide. Next one. So this is the beginning of what we're looking at in terms of building an architecture that is event-driven. And again, sometimes you look at events, if you look at logs from a specific website, that's easy to do event analytics on that. But what we're really speaking of here is looking at events from different modalities, different applications, and being able to create that thread. So what you see here from the left side is social sites, email, display advertisement, transactions on the website, products or even recommendations, different JavaScript libraries that you may have on your site. Each one of them, they do their own tracking and being able to capture that into what we call an event repository. And then what happens is that event repository is we add metadata to that. We could use, for example, it could be a JSON format, and you can add headers to that information and make them an agnostic event repository that they all look like different types of event, but they have the same format. Next slide. And then in terms of the type of analytics you could do on a data like this, one way to do that would be creating in-path analytics. You could do graph analytics, looking at a relationship between different customers or relationship between the different apps and the customer. So there's many different ways of analyzing this data and be able to also display it beyond really a typical BI tools and more into graphs and in-path and interactive GUIs that you can think of. Next one. And another part of what you could do with this data is to create a dashboard. It could be a reporting dashboard that can, again, deal with the data that comes in. Some of it is real-time, some of it is batch-oriented, and be able to look at those raw events or be able to do simple analytics on your event repository and be able to create reporting on that directly from your repository. Next. And then a final component of this architecture would be some type of a modeling, machine learning. So be able to look at these events and then be able to extrapolate what kind of a recommendation you should make, for example, or how do you optimize your marketing channels, or how do you change the way you do email marketing, looking at the whole picture of the different customers' experience on your website and the outcome. Obviously, if you look at this behavioral data, at some point, you're either able to convert the customer or not, and that all of that can go into this machine learning. Again, obviously, this is a batch-oriented machine learning process that can then feed back into the whole ecosystem. Next slide. And in terms of, and a little bit getting more into the actually how you would do something like this, the first element of that is on the left side, you're looking at a batch ingest. So this could be FTPs, it could be something like Flume, or it could be some type of product that you would build in to be able to capture, to bring these events on a batch-oriented mode into your event repository. And some of the challenges there would be around, for example, making sure your events are large enough if you're dealing with in a batch-oriented way before you transfer them to the event repository if it's HDFS, for example. So there's a bunch of concerns that you have to be worried about on that batch ingest process. Next slide. If it's a streaming ingest, then you also have different types of technologies. You can think of RESTful APIs that could, for example, go into Kafka or some other message queuing, and then being able to process that using Spark streaming or Storm. And depending on your level of processing, then either deposit those events as raw events into your event repository or do some level of processing, for example, annotating them or making them into a common format. All of that could be done in the Spark streaming. But at the end of the day, really, you have these events of different nature, of different applications coming in all together into an event repository of different nature. You know, some could be batch, some could be stream. Next slide. And in terms of the type of products that you would need to deal with, about different types of processing in that event repository, which typically could be it could be your Hadoop, is really Hive would be the tool that you would use for the processing and of those events, and then being able to also sometimes HBase, if you're landing the data from your Storm, that could be the place that you put the events, and then you can do some type of analytics around stitching together all these different events across different customers and being able to create that type of a chart that we had before. All of that could be done in this layer. Next slide. And then obviously all of this has to have a data dictionary, and that's an important part of the whole story, is to be able to capture metadata and retain that over the cycle of what happens to those events, the raw events that we capture. Next. Another element of this, in terms of the processing and the empath analytics and the GUI, would be something like an analytic engine, event metadata dictionary, and processing that could end up with giving you that empath of the events as they go through different funnels. Next slide. And the data warehousing could be part of this. For example, let's say you have your reference data, for example, customer data, product data, transactional information that you captured from your different databases. That data can also be combined with your event data, so it could be part of that architecture as well. Next slide. And then the other component of this architecture is a dashboard engine, which would be a dashboard engine directly against your Hadoop database, and that would then, your BI tools would go against this dashboard engine that can, for example, you can look at them as OLAP or dimensional tables or different ways of looking at that event as time series data within your dashboard. Next slide. And then in terms of your event processing, in terms of machine learning, there's many different ways to look at how you can, in a real-time or batch-oriented way, and in this case mainly was batch, to be able to make decision-making on those real-time and batch data that you captured. And I think the final slide. And then the matching of scores, and for example, this could be scoring of finding different patterns in your events, or being able to do some kind of prediction or classification or some kind of a regression model of these events that you captured. All of that could then go into your Spark or any other type of R or any other processing engine that you have. And I think that's the final slide. Next one? Yes. So any questions for either part? Go ahead.
Since you're just
We have, okay. It's not a conceptual diagram. We actually are, this final diagram we showed is based on some of this. We already have products around it. So because of the nature of this conference, I didn't want to put actual product names against those components. But in this case, we are using Spark streaming. So we're using Kafka and Spark streaming, and we're also using Elasticsearch for the metadata part of that and ingest. So it's an actual event, a real-time event ingest product that we're building around those technologies. So yeah, this is not some, it's not just an idea. There's actually products at different maturity level around this ecosystem that we're talking. Between Storm and Spark streaming, I think we have good publications around that. The main difference that I can think of is Spark streaming is macro batches, and Storm can deal with one event at a time. Storm also has macro batch if needed, but really Spark streaming is mainly macro batches, and it works better with the whole Spark ecosystem. So, but yeah, there's trade-offs. I don't have the right answer. Thank you very much.
Okay. Thank you.